In the last lecture, we have seen that scientists found evidences for the nuclear shell model, and the shell closure was supposed to be obtained at the 2, 8, 20, 28, 50, 82, and 126. These are called as the magic numbers. What is the meaning of the magic number? That the shells are supposed to be closed at the neutron number 2, 8, 20, 28, and all. Okay, so the nucleus which are having the nucleon number shown by these figures, they must show, or they are showing the different properties than their neighboring nuclei. Therefore these are called as the magic numbers. And now scientists tried to find which potential will be going to give these magic numbers. For the development of this nuclear shell model, scientists tried infinite square well potential. So this is infinite, this is infinite. So they tried the infinite square well potential, and for this infinite square potential we can write this V is equal to 0 for R greater than R naught, and V is equal to minus V naught for R less than R naught. Okay, but in Editron it was a square well potential, but it was finite square well potential. For the development of the nuclear shell model, actually scientists tried many potentials, but they started with the infinite square well potential, and mathematically it could be represented by V is equal to 0 for R greater than R naught, and V is equal to minus V naught for R less than R naught. Okay, then afterwards they write Schrodinger's time independent equation for the square well potential. During this deuteron, we have considered the potential as a central potential. So the central means it was independent of theta and phi. But now they have considered the wave function psi is a function of r, theta and phi. So for this wave function psi, which is a function of r, theta and phi, which is a not central, so for this wave function, the Schrodinger's time dependent wave equation could be written as minus h cross square upon 2m d square u upon dr square L into L plus 1 h cross square upon 2 mr square u is equal to E of u. Okay, by solving these equations or getting the solution, what you are going to get? You are going to get the values of n and l. Okay, now l is a orbital quantum number and n is a principal quantum number. Okay, so l is equal to 0, n is equal to 1, 2, 3. For l is equal to 1, n is equal to again 1, 2, 3. For L is equal to 2, so this again n is equal to 1, 2 and 3. Here we can see that the relation between the principal quantum number n and orbital quantum number L is not same as that of the atomic and molecular physics. So in a nuclear and particle physics, n is a principal quantum number, L is a orbital quantum number, but the relation between the principal quantum number and orbital quantum number is like this. So for the values of L is equal to 0, 1, 2, 3, 4. So this will be S, P, D, F and G. So by solving this Schrodinger's time independent equation, actually there are a lot of tedious mathematical calculations over here, and after that you are going to get these values. I have written those directly. Okay, because we just want to see the development of the actual nuclear shell model we are using right now. Okay, so the calculations are out of scope of this syllabus, so I am not going into the details of these. Okay, you just understand that. So this is the relation between the principal quantum number and orbital quantum number, nuclear and particle physics. Okay, So after this, the scientists tried the harmonic oscillator. Why? Because from this also the shell closure was not obtained at 2, 8, 20 and 28. Okay, so again they tried some new potential. So this potential was infinite square well potential. Okay, then they tried some harmonic potential. I'll write it here. Okay, so for that the same equation could be written as Schrodinger's time independent equation. So this term will remain same, d square u upon dr square plus, so this v of r, so that will be here v of r is remaining, v of r plus this term is there. So this will be 1/2 m omega square r square. So this is the harmonic potential. This is a non-central part which is also present in this equation. 2 pi r square h cross square u is equal to EU. In a deuteron potential we have taken the same equation. So this part was only V of R, because here we have considered the potential as a central part. Now here we are considering the non-central part above this central part, and here we are considering the infinite square wave potential which is harmonic also. As the Schrodinger's time independent equation changes, the solution for these will change and the values of this n and l will change, and along with that the magic numbers will change. So the scientists keep on experimenting and taking different potential values unless and until they found this all these magic numbers. For this they came to know that, or they thought that this infinite square well potential is not a good idea, because at that time also we know that the nucleon can be removed from the nucleus. Okay, so that the potential well could not be a infinite square well. So they tried for the finite square well potential, and they did the same procedure. Okay, for that also they didn't get the magic numbers. After that they tried Wootz section function. Okay, so now what is this Wootz section function? So after this finite square well potential, they found that, or they thought that the any function, so that is not changing drastically. Okay, there is nothing like that. Suppose the point is there up to here, its potential, and potential is 0 over here. Okay, up to this boundary there is some potential, and after this point the potential drops drastically. Okay, this is not the case practically. Actually the potential, force, energy, whatever the entity, whatever is the function, that function goes on decreasing gradually. Okay, so the Wootz section function is the mathematical representation of the exponentially decaying potential. Okay, so the scientists tried for the Wootz section function, and which made the energy level shifted little bit at the higher level. Okay, but still they are not getting the magic numbers. Now along with this Wootz section function, they took the L dot S term. Okay, so we know that this L dot S term is nothing but the relation between the orbital quantum number and the spin quantum number. When they use the Wootz section function, Along with this L dot S term, they finally got the magic numbers. And from that we can say that the potential in the nuclear shell model could be of the Wootz sanction function along with this L dot S term. Okay, now by using this term, okay, by writing this Schrödinger's time independent equation and solving it for n and L values, they found that for L is equal to 0, this total orbital angular momentum is equal to 1 half, and for L is not equal to 0, that J turns out to be L plus 1 half and L minus 1 half. Splitting of the energy levels. Okay. In these two energy levels, we can see that for L is not equal to 0. So this L, that energy level is split into two energy levels, which is one is L plus 1 half and another is L minus 1 half. Out of this, L plus 1 half is a more stable and it is shifted downwards, okay, and it is having more energy, so therefore it is shifted upwards. Okay, so L plus 1 half is downwards and L minus 1 half is upwards. Now this Wootz action function along with this L dot S term will give the energy levels like. Now the energy levels by using the Wootz action function and this L dot S term are given by. So let us see, I will draw here first one S orbital, then here it will be 1p, 1d, 1f, 1g, 1h, and then 1I. Okay, so for this I will write it here. This L is equal to, for this term L is equal to 0. I will write that table here. For L is equal to 0, 1, 2, 3, 4. Okay, for L is equal to 0, it is called as a S. Now I am going to write that table. For L is equal to 0, 1, 2, 3 and 4, which is S, P, D, F and G. So as this L is equal to 0, so it will give you J is equal to 1 half. For this P, L is equal to 1. So this L orbit or L energy shell will be split into L plus 1 half, that is 3 by 2, and L minus 1 half, that is 1 half. Okay, then D, for D energy shell we are having L is equal to 2, therefore 2 plus 1 half, that will give you 5 by 2, and 2 minus 1 half, that will give you 3 by 2. Similarly, this F, for this F energy cell, L is equal to 3, so it will give you 3 plus 1 half and 3 minus 1 half, which is 7 by 2 and 5 by 2. This G orbit will split into 9 by 2 and 5 by 2. So now let us draw the energy level diagram by using this single particle exchange model, by using the Wootz action function and the L dot S term. So first it will be 1s, 1p, 1d, 1f, 1g, one H, and here it will be one I. So this is 1s, 1p, 1d, 1f, 1g, 1h, and 1I. So it will be L minus 1/2, and this is more stable, and therefore this J L plus 1/2 will be shifted downwards. So first write down these energy levels. The relation between the energy levels in a atomic and molecular physics is not same as that of the nuclear and particle physics. Here we can see that we have all the energy cells as 1s, 1p, 1d, which are not present in a atomic and molecular physics. Okay, so these energy levels are very easy to draw. Just write down 1s, 1p, 1d up to 1I. Okay, then leave this 1p and start here 2s, then 2p, 2d, 2f, and 2g. Okay, then leave this 2p and start 3s over here. 3s, 3p, 3d. Okay, you have to remember that the splitting between the p orbitals is smaller than that of the d orbitals. Okay, for example, this is a splitting between the two p orbitals, then the splitting between the d orbitals must be greater than that, and for f it should be more than that. So this is for the p, this is for the d, this is for the f. So for the g it will be again more. Okay, so it means that as the value of L goes on increasing, okay, I'll write the equation. As L increases, splitting increases. Okay, so while drawing the diagram, you just remember this thing. Okay, so the 1s orbital, it will not change, it will not split, so it will remain as it is, as 1s 1/2. Okay, now this p orbital will split like this into two energy shells, which are 3/2 and 1/2, out of which this 3/2, which is L plus 1/2, it is more stable and it is shifted downwards. Therefore we write downwards 1p 3/2. After that we are going to write 1p 1/2. Okay, similarly, so this d will split into 5/2 and 3/2. As we know that the shifting between the, or the splitting between the p and d orbitals is different, we have to show it. So I am showing it little bit more like this. So d 5/2 will be moving downwards due to the more stability. So I will write it here 1d 5/2, and here it is 1d 3/2, and here it will be 2s 1/2. Now similarly, 1f will have more splitting than that of this d orbital, so which I will show here further. So this is the f orbital, splitting will be more for this. Okay, so this f orbital will split into 1f 7/2, 1f 5/2. Again there is a 2p orbital, so this 2p orbital will split into 2p 3 by 2 and 2p 1 half. Okay, so all the things should be in the same vertical plane, but here I cannot show that, so therefore I am showing it on the a little bit ahead of this. Okay, but all the energy levels should be in the same vertical column. Okay, so you just draw it in your notebook properly. Okay, or I will show from my notebook how it should be. So this is now G energy level is there, so G should have more splitting than that of the F, so I should show it like this. You just understand the method how to draw this figure. Okay, so this is 1G 9 by 2 and this will be 1G, here it should be 7 by 2. Okay, 1G 7 by 2. Along with this d orbital is there, so this is d is splitting into 2d 5 by 2, 2d 3 by 2, and then 2s orbital is there, 2s 1 half. Okay, after that splitting of this h, again we are going to increase the splitting between G and H, so splitting of the H should be greater than that of the G, so H is splitting into 11 by 2 and 9 by 2, so I will write it here, 1H 11 by 2, 1H 9 by 2. Along with this 2F is there, so F we have shown this much, so this is 2F 7 by 2 and then 2F 5 by 2. Then here we can see that this 3p, so p orbital is again splitting, so this will be 3p 3 by 2 and 3p 1 half. Okay, similarly you can split this 1i orbital also, 2g and 3d orbitals. Okay, this is the diagram which is so this is the diagram which I have drawn into my notebook. So here you can see that. So to draw the energy diagram of the nuclear shell model by using this single particle exchange potential, you need to know the relation between L and N in a nuclear and particle physics. You must also know how these energy levels are splitting into L plus 1 half and L minus 1 half, and along with this you must know which are the energy levels in the nucleus. Okay, once you know this energy level diagram, you can calculate the spin parity of any nucleus in the periodic table. Along with that, you can also state the excited states of the nuclei.